Good day everyone. So for today we're going to learn how to solve first order homogeneous differential equations. Now before we try solving this particular type of first order differential equation, we need to first define what a homogeneous function is. So we say a function of x and y is said to be homogeneous of degree n if there exists a constant n such that for every quantity r, which could either be a variable or constant, the function of rx and ry is equal to r raised to n times the function of x and y. Now, this function of rx and ry is to be interpreted in a manner that your variable x should be changed to rx and your variable y should be changed to ry in your given function. After that, you try to factor out the common factor of r in all the terms of your function after you have changed all your variables. Then, if the resulting function is the same in form, exactly the same in form as the original, after you have factored the expression of r raised to n, then your function is said to be homogeneous of degree n. Now, this particular concept of establishing homogeneity of a function is illustrated by the two examples here below. So in the first example, we have x squared plus 2xy plus y squared. So what we're going to do here, we're going to replace x by rx and y by ry, and we do just that in here. Now constants will remain as constants, so we don't change them. Only the variables are to be changed. Now after that, as I have said, we will factor out the common factor of r in all the terms that we have altered by changing the variables. So in this case, the common factor is r squared in all your three terms. If you factor that out, what you have left is x squared for the first term, 2xy for the second term, and y squared for the last term. Now, if you look closely at this particular expression, it's exactly the same as the first or the original that was given. So in this case, we can conclude that your given function is homogeneous of second degree or of degree 2. The given function is homogeneous of degree 2. Now, let's look at the second example here. Now, let's say, for example, we will not change the variables x and y to rx and ry. So, we will simply check homogeneity by method of inspection. What do I mean with method of inspection? You have to add all the exponents of the variables that appear in your equation. If this sum of exponents of your variables that appear in the terms of your equation are the same, then your function is said to be homogeneous with degree equal to the sum of the said exponents. So in our example, it's 4 for the x, 1 for the y. So that would be a 5. And the second term, it's 5 for the y only. So both terms have the same sum of exponents for the variables. That is the case, our function is homogeneous of degree 5 because that is the sum of the exponents of the variable in the first term, and that is the exponent of your variable in the second term. Now, if you want to follow crudely the procedure that was illustrated in the first example, we will still see that the common factor is r5, and after factoring the common factor, the remaining expression is the original given function. So we can conclude that our given function is homogeneous of degree 5. Now take note that for polynomials, they are said to be homogeneous if all terms are of the same degree. Not just one, not just two of your terms, but all terms of your given polynomial are of the same degree. Now that we have learned how to establish homogeneity of a given function, then we are ready to proceed to knowing how do we find solution of homogeneous first order differential equations. And let's go to the next slide. So let's say, for example, we are already given a differential equation of the form m of x and y dx plus n of x and y dy equal to 0. Now we say that this particular differential equation in this form is homogeneous if and only if the degree of both m and n are equal, and at the same time m and n are homogeneous. So number 1, m and n are to be homogeneous, and second condition is m and n should have the same degree. Now, let's look at the example here so that we will understand better this particular concept of homogeneity for a given differential equation. Now, you're given this differential equation, square root of x squared plus y squared plus y, quantity dx, plus x dy. By inspection, you can right away look at the second term, and its corresponding degree is 1. It has only one term, so there's no need for us to check for homogeneity because we only have a single term there, of course aside from the dy. Now for the m of x and y, if you look at this plus y here, it's of degree 1. Now if we look at the square root, both terms inside the square root is having a degree of 2. But since it's under the square root sign, we're supposed to divide the exponent of the variables under the given square root by 2, because square root means 1/2. So if we do that, the degree then of this term in the square root sign is also 1, because it's x squared plus y squared. If you take the square root, or rather if you take the half of the exponents 2 here in the two variables, that would be 1. So in that case, then we say that the degree of this term and the second term are just the same. So then we conclude that our DE is homogeneous of degree 1 because your m is of degree 1 and your n is of degree 1. So that's it here. Homogeneous of degree 1 for n, for m homogeneous of degree 1 as well. Both functions of the differential of x and differential of y, I mean the functions multiplied to these two differentials, are homogeneous of the same degree. And as such, then we can conclude that our DE is homogeneous. Now, upon establishing the homogeneity of your differential equation, you know already that it's homogeneous. What's the next thing that you should do? Then you are going to find the solution of your given DE already. So the first thing that you should do always is to establish homogeneity of your first order differential equation. If it's homogeneous, then apply the procedure in determining solution of first order homogeneous differential equations. Now, in terms of the solution, there are two methods that could be used, and each method has a 5-step rule to follow. So if one will not work, then you go to the other. But I think for any homogeneous first order differential equation, any of the two methods will work. Only that one method might make the solution simpler over the other. So we will check in a little while what method will you choose if you're given a particular differential equation. So on the left side, you have the method 1, and on the right side, you have the second method. In method 1, you are to assign, or you are to create a new variable v, which is equal to y over x. Now, this particular variable v is arbitrary. You may change this to any letter that you like, but in most textbooks in differential equations, it's always v that is being equated to an expression containing the variable x and y. So the first method says that we create a new variable v which is equal to y over x. Then, after that, from this expression, we express y in terms of x. How is that? So, you keep y in this side and you cross-multiply x on the left side. So, that would be y now being equal to bx. Now, with this particular relationship between x and y depicted in the equation containing the v, we will go back to our given dE and replace all the y's that you see in the equation by vx. What do I mean all the y's that you see in the equation by vx? The y in the dy dx you will change to vx. And the y that you see in your dE, and that's the fourth procedure, you also change to vx. Now, since you are changing your y in the derivative dy dx by vx, it's written here, you are to apply the product rule of differentiation. Why? Because you see here, you change y to vx, and you're going to take the derivative of that. So, what's the rule, or what's the product rule of differentiation? It says, the first term times the derivative of the second plus the second term times the derivative of the first. In that case, all of which would be in terms of the independent variable x. So, your first order homogeneous differential equation will have to be changed. The derivative of that will have to be changed to this particular expression, aside from changing all the variables in the equation by vx. So, correspondingly, all y in the equation should be changed as well. After you're finished with integration, you are to replace all the v in the resulting solution of the differential equation by y over x. So, meaning, since you have created this variable v equal to y over x, this v is going to appear in your solution later on. So, since your dE does not contain a v, you are to resubstitute what the v represents. So, all the v's in your final solution for the dE will be changed to y over x. The second method is quite the same with the first, only that we create an expression of x in terms of y. In here, it's v in terms of y over x. In here, it's x in terms of y. Again, we use the v variable. You will also have to change all the x in your equation, in your differential equation by vy, just like what you have done here. And you will, of course, change the derivative of the differential of x rather in your derivative or in your dE by v dy plus y dx. Why? Because this x has to be changed to vy. And if it's changed to vy, then you are to use product rule. So, first term times the derivative of the second plus the second terms times the derivative of the first. So, the x is changed to vy, and you are to apply product rule to the expression vy. So, in your original dE, you will change the differential of x to this, and you will change all your x to vy. After you're done with integration, and you see v's in your final answer, change that v to x over y. That's how we solve homogeneous differential equations. So, notice class that v, as I have mentioned a while ago, is an arbitrary variable that you will place in here together with your original variables x and y. If you want a different letter, then do so. If you want to replace v with any letter that you like, then you can do that as well. Now, since you have two methods here, what tells you which of the two you will use? It's not something that you do try and error. It's because the procedure in itself is inherently lengthy or long. So there has to be some guide as to which of the two methods you will use. And this is the guide here. If the m expression is simpler, you use this particular relationship that you will change x for. So you change the x to vy in your original DE. If it's the other way around, if n is simpler, then use the y equal to bx representation, just like this. So it's either x is equal to vy or y equal to vx, depending on which expression is simpler. The expression that I mean is the expression multiplied to the differentials x and y in your differential equation. Now, let's look as to examples that will illustrate how we find solution of first order homogeneous differential equations. Now, if this DE is not written in the form m dx and n dy, but if you will do that by inspection, you can transfer differential of x here and you can transfer xy here, and that would lead you to seeing that the expression multiplied to the differential of y has a degree of 2, because if you take the sum of the exponent, it's 2. Now, let's inspect as to the terms that is pre-multiplied to the differential of x if you transfer differential of x here. And that would be x squared, second degree, and y squared, which is also second degree. Since both expressions have the same degree and are homogeneous, then we say that this differential equation is homogeneous. That is by way of inspection. It's just like you do it with the use of your eye. You did not write it anymore, and you get to see that, this one is second degree, this one is second degree, this one is second degree. All my terms are all second degree. Then my DE is homogeneous. Now, but there's another approach that we could do since we already assigned V equal to y over x. Then we will substitute. We can substitute that particular, or we will make use of that particular expression in this particular DE that is given to us. So let's say, for example, you treat the DE on the expression on the right side of the DE in this manner. Distribute the divisor. By rule of algebra, what remains in the first term is xy, and what remains on the second term is yx. Now, this xy is actually the reciprocal of yx. So in here, you have yx. We copied yx. And then, this is xy. But notice that it's written as yx raised to negative 1. What does this mean? That if I will put this one in the denominator of my fraction because it's negative 1, meaning this whole expression is in the denominator, the resulting expression would also be this. The purpose of writing it in this manner is that we could replace this one by v right away based on the first method that we have discussed, that v is equal to y over x. So we have a function now of y over x. So it's important, class, that you see that we have manipulated x over y into its equivalent y over x here. And it was raised to negative 1 so that it would still be equal to this one. Now, if we go back to our DE, it's dy dx. This one now replaces this. And it's y over x raised to negative 1 plus y over x. Then what we do? We change the y to vx in the dy dx expression. If you do that, your y here being changed to vx will yield to this particular expression. If y is changed to vx in your differential of y, it will yield this particular expression. The question is, why miss? Why would it yield this one? So you apply product rule. If you apply product rule here, it would be v dx over dx plus x dv dx. This is what you're seeing here. Again, product rule would be v dx dx plus x dv dx. That's this one. Okay, I'm not looking here, but I'm looking here and trying to use product rule. So I change now the dy dx to this equivalent expression. Then the y over x here, which is raised to -1, will have an exponent of -1, and this is your v. Then if we subtract v on both sides of our equation, or simply algebra tells you that if a particular expression is present in both sides of your equation, you can do cancellation. What remains is x dv dx equal to v raised to -1. If you look at this very closely, this is separable. Why is it separable? You can transfer this v raised to -1 here. You can transfer dx here and divide it by x. So what do I mean by that? This one. Now it's integrable. So we can integrate. This would be v squared over 2. And this one would be an ln of x plus c. Now let's remember one rule when we perform integration in DE whenever we see an ln term. If an ln term is present in one of the terms of your solution for your DE, the constant should be replaced or could be replaced by ln of c. So if we will replace this one by ln of c, then we have ln of k, or we can change c to ln of k, so that we can combine these two ln's with just one expression, the ln of kx. That way, when we simplify later on, we won't have a lot of variables to bring about. Again, this c could be written as ln of another constant. So it could be ln of k. Why? Because we have a term in our solution that is an ln. If you don't have an ln term here, then it would be a simple c for your arbitrary constant. Okay, so we made use of the property of the ln here to simplify the ln of x plus ln of k to this expression. Now, do you remember the manner in which we write our solution explicitly? So I want v to remain here. So I transfer the 2 on the other side, so that would make this side 2 ln of kx. And I want v, not v squared. So what do? I take the square root of both sides of this equation. So if I take the square root of v squared, that would be a v. And this one here will be positive negative square root of 2 ln x. The last procedure is for you to change your v to y over x. So we do just that. We change the v here to y over x equal to plus minus the square root of 2 ln of x. Again, I want y to remain here in this side so that it would be explicitly written. I'm referring to the solution of my DE. So I will just transfer the x on the other side. Multiplication, not addition. So now it became, the solution became plus minus x square root of 2 ln of kx. Now, this one you have seen in the document that I uploaded in Canvas as to how to determine the solution of a homogeneous differential equation, because this is one of the examples there. I want you to look at this and study this in your free time. I will place this particular recorded video in the discussion part of Canvas, and I'd like you to place there in the form of replies any questions that you may have in here, because this one was already given to you in advance to read and study. I really welcome questions and points of clarification there. That way I know that you are studying what you're supposed to study, or you're reading what you're supposed to read. Anyway, these two are there already in your document, so you please kindly read the document. The procedure that is outlined here is exactly the same as the one that I have just discussed a while ago. Okay, so this is the end of our topic for first order homogeneous differential equations. Please drop your comments, questions, point of clarifications in the reply box in the discussion under this link in Canvas. Thank you for listening.